So welcome to the next video. So in this video, I am trying to solve another KTU problem. This was asked in 2019 December for 10 marks. This is from MoS, Module 4. In Module 4, this is particularly from the bending moment equation, bending stress equation portion. Okay. Now the question is, a beam of I section 200 mm wide, 300 mm deep with flange and web thickness 20 mm is used as simply supported beam over a span of 7 meters. The beam carries a distributed load of 5 kN/m over the whole span and concentrated load of 20 kN at the midspan. Determine the maximum bending stress setup and sketch the stress distribution. Okay, right. So what it's given is it's an I section. So quickly I'll draw the I section here. It is 200 mm wide and 300 mm deep. So this is 200 mm. So this is 200 mm. And 300 mm deep. This is 300 mm. Okay, so when you say depth of the dissection, it is actually the total depth of the dissection. Then web thickness is 20 mm. Flange and web thickness is 20 mm. So this is 20 mm. This is flange 20 mm. Web is also 20 mm. This is also 20 mm. So web and flange thickness are 20 mm. So it's a regular dissection. Now it is to be used as a beam. It is used as a simply supported beam. So one end is pinned, other end is roller. Then there is a load on the beam. It is telling it's a 5 kN/m UDL. So this is 5 kN/m UDL and a concentrated load of 20 kN. Okay, at the center. Okay, now there are two loads. I think it is better if you calculate the bending moment and shear force. So bending moment will be maximum at the center because of the symmetry. So what we will do, we will first find the reactions. So quickly we can find the reactions. So this I will call as A, this I will call as B. So here I will call vertical A. Here I will say it is vertical B. There is a horizontal force here which is coming to be 0 because there is no horizontal force here. So let's say if I take because of the rotational equilibrium, okay, rotational equilibrium gives sum of all the forces, all the moments about any point equal to 0 for this structure. So that because it is not rotating, so about any point you find the moments, it should be adding to 0. So let's say we will say sum of all moments about A equal to 0, and we will assume clockwise to be positive. Okay, so that means we have, what is the dimensions? We will just draw the dimensions also here. So this is totally 7 meters. 7 meters, and point load is at 3.5 meters. Okay, now quickly we have 20 kilonewton into, so about A we are finding 20 into 3.5 is the moment due to 20 kilonewton, and remember it is trying to rotate in clockwise direction, so it's positive. Then we have the UDL is, the magnitude of UDL is 5 into 7, and it is acting at the center. The resultant will be acting at the center, so the moment will be 3.5. Okay, then we have this also clockwise, so positive. Then we have VB into 7. Now VB is trying to rotate in anti-clockwise direction, so it's minus equal to 0. So that means VB equal to 20 times 3.5 plus 5 into 7, 35 times 3.5 divided by 7. So this we can calculate very fast. So 20 times 3.5 plus 35 times 3.5 divided by 7. So it is 27.5 kilonewton. 27.5 kilonewton. So that is a force reaction at the end. Now, because of symmetry, we can also write VA is also same value, or you can say vertical equilibrium. We can write vertical equilibrium. Vertical equilibrium. It is VA plus VB. So let's say upward positive. Sum of all forces in vertical direction equal to 0. So upward positive VA plus VB minus 20 minus 5 into 7 equal to 0. So VA plus 27.5 equal to 20 plus 35. So VA equal to 55 minus 27.5 equal to 27.5. Okay, so reactions are 27.5 each. So we'll find the moment at the center for maximum. Maximum moment will be at the center. So let's find the moment at center. So what we have here is, this is 27.5. Then this is 5 kN per meter, and this is 3 meters, 3.5 meters. Okay, so we can have a moment here, and we can also have a shear force here. I'm not drawing the shear force because the moment is only what we need. Okay, so that I call as M. So summation of all moment at let's say about A or B, let's say about B, or let's say B dash, about B dash equal to 0, clockwise positive, clockwise positive. So that is 27.5 into 3.5 is the moment due to this. So I am trying to find moment about this point. Now what is the rationale behind this equation? It is simple. Since the beam is not rotating, a portion of the beam also will not rotate. Okay, so this I have taken the portion of the beam to find the moment here. So moments are internal forces. To get internal force, you have to always cut the section. So that is what I have done. Now about this point, we will try to find moment because so there's a shear force here. Shear force, I am just ignoring it. There's a shear force here. So since I am finding moment about this point, I can ignore the shear force because this shear force is passing through this point. Now clockwise positive, 27.5 into 3.5 is moment due to reaction, and 5 kN UDL it is 5 into 3.5 into 3.5 by 2. So this is in anti-clockwise direction, so it's minus, then minus M equal to 0. So that means M equal to 27.5 times 3.5 minus 5 into 3.5 square by 2. Now what is this value? This comes out to be, so 27.5 times 3.5 minus 5 times 3.5 square divided by 2. So this gives me 65.625 kN. 65.625 kN. Now there is another way of doing it. All these complications we can actually avoid. Only thing that you have to know is, you should know that what is the maximum moment for UDL and a point load at center for a simple supported beam. So we can do this like this. So this is what I prefer. Instead of doing all this calculation, we have a UDL here. The value of UDL is 5 kN per meter, It is 7 meter span. Then we have the bending moment like this. So this will be the bending moment diagram. The maximum bending moment will be at the center, that is WL square by 8. So this is nothing but 5 into 7 square by 8. So what is this value? 5 times 7 square is 49 by 8. So this is nothing but 30.625. 30.625 kilonewton meter. Okay. Now the second scenario is point load. Point load. What is the point load? The point load value is 20 kilonewton. It is at the center. So this is 7 meter. This is 7 meter. And this is 3.5 meters at the center. So point load the moment looks like this. Maximum again at the center. Now the center, that value is WL by 4. So that is nothing but 20 into 7 by 4. So 140 by 4. So it's nothing but 140 by 4 is 7.2, that is 3.5. So 140 by 4. So 35 kilometer. 35. Okay. Now if I add this, what I'll get, the total moment is, I'll just add these two. So moment is nothing but 30.625 plus 35, that is 65.625 kilonewton meter. So this is easier, the same moment I have found, but this is by superimposition. Okay, with both loads I am separating. So we expect to do like this. This is faster. In 2 minutes I have found this. Instead of finding all the reactions, this is the right way to do it, but when the load is not symmetrical and all. But since when load is symmetrical, you always try to do this. These two formulas you should remember, WL square by 8 and WL by 4. Now so so this is a maximum moment. Now what they are finding is, you have to find the bending stresses. Okay, so bending stresses because of 65.625 kilonewton meter moment. Now bending equation we can use. So bending equation, it is m by I equal to sigma by y is equal to E by R. Now this you can remember by may I see you Elizabeth Rani. So imagine that you are going to meet Elizabeth Rani and you are asking for permission. So may I see you Elizabeth Rani. Okay, so this is something which you can always use. And now what is the y? Y is the point from neutral axis where you want to find the stress. Okay, so this I'll use this again. Let's take this. So I'll erase this here, or I will draw the. So this is a symmetrical section. So neutral axis will be at the center. Then neutral axis will be at the center. And I am just drawing a line at the extreme ends. Okay. So drawing a vertical line. Now the top of the beam will be compression, under compression. So I'll draw compression here. The top of the beam will be under compression. Bottom of the beam will be under tension. Okay. Now so this is done. Now for maximum tensile stress, so from here we will measure y. So for maximum tensile stress, we can measure y downward. So for maximum tensile stress, the y should be this value. So I'll call this as yt, will be equal to 300 by 2, that is 150 mm. Okay, it is symmetrical section, so centroid will be at the center. So maximum for tensile, the y for location of tensile stress maximum is in the edge. So all these points in the edge, in the end, bottom end will have maximum tensile stress, and all the points in the top end will have maximum compressive stress. So this I'll call as YC. So YC equal to again 150 mm. Okay. Now we just use the bending equation. Bending equation is, so remember what is this bending equation? Bending equation gives the moment, relation between moment at a section and the stresses in the section. Okay. So moment at the section we have found, we are just finding what is the stresses at the center. At the center, the moment is 65.625. Because of 65.625 moment in the center, what is the stresses? Okay. So we just use the first part of the bending equation. Substitute the value of y to get the stresses in location. So if you want to find stress at this location, you find this y. This y you substitute in this equation, you get the stress at this location. So that is how this equation works. Okay. So let's say m by I. So sigma. So let's say we'll take compression. So extreme fiber compression or compression maximum. So m by I equal to sigma compression upon yc. So sigma compression equal to m by I into yc. So now we want to find the value of I. Value of I, it's a symmetric section, so we can find very fast. What you do, you first find the I of this value, this full rectangle, that is 200 into 300 cube by 12. Then from that you subtract a rectangle made of these two cut portions. Okay, since the cut portions are symmetric about this axis, we can join them and write. So basically it is this, what is this distance? This is 200, 200 minus 20, 200 minus 20 is 180. Okay, 180 into, this is 300, 300 minus 20 minus 20, 300 minus 40 is 160, 160 cube by 12. Okay, so this is how you find the moment of inertia of symmetrical I section. If this I section is symmetric, then we can use this formula. Now what is this value coming out to be? So we'll quickly calculate that. That is 200 times 300 cube 12 minus 180 times 160 cube by 12. So this comes out to be 388560000. So 388560000 mm to the power 4. Okay, now just substitute the value. What is the value of moment? Moment is 65.625. Be very careful. Here you have to convert the moment kilonewton to meter. So to convert kilonewton to meter, you have to multiply by 10 raised to 6. Okay, yc is given 150 divided by 388560000. So what is this value? This value is nothing but, so let's calculate that, 65.625 into 10 to the power 6 into 150 divided by 388560000. So this gives me 25.33, 25.33 MPa. So this is a compressive stress. So since I know this compression, I'm not using any sign convention here. Compression, so I'll just 25.33 MPa as compression. So it's basically negative. We are not disputing the sign. Now tensile stress. So tensile also we can find like this. Tensile stress at extreme fiber. So we can say m by I equal to sigma tension upon yt. Okay, so sigma tension equal to m by I into yt. So this is nothing but 65.625 into 10 to the power 6, same moment, into 150 upon 388560000. So this is same. So same value will get 25.33 MPa. So here it is 25.33 MPa tensile, and top it is 25.33 MPa compressive. Okay, so this is how you solve this kind of problems. Check the calculation. I am directly doing this calculation online. I hope there is no mistakes here. But I hope how to solve this problem. So first you have to find the moment, then you just use the bending equation. These two is the main component when you see from outside. Okay. So I hope you will be able to solve this when it comes, this kind of problems comes in your exam. Thank you. We will solve another problem in the next video.